So we're going to look at some some application problems. Some of them are finding maximum minimums, and some of them are going to be dealing with rates of change. And we can use derivatives to do both of these. And keep in mind, in real life, there are lots of examples of manufacturers of canned goods or drinks, or they need to minimize the cost of the manufacturing, or they're going to maximize the profit. These are common problems for people to really have to do. In this problem, they tell us that the surface area of a solid cuboid is 100 centimeters squared and that the volume is V centimeters cubed. They want us to express H in terms of X. They want us to show that the volume is this equation. And then, given that X is going to vary, they want to find the stationary value for the volume that's defined a maximum or a minimum. All right, so let's go ahead and map out a strategy. What we're going to do is we're going to find that in these kind of problems that it's got volume, there's three dimensions. For example, in this case, the volume is going to equal x squared times h. Well, if we're going to find the derivative of an equation, it only can have two variables, input and output. So what we're going to have to do is we're going to have to rewrite this so it only has x's. So you'll notice how they gave us surface area in the very beginning. We're going to use this. Now we know that the surface area is 100. And we can figure out that, because that's all that is all these 6 areas added up, and the opposite ones are the same. So when I do that, I can simplify this, getting h by itself. I'm going to end up with this. Now this is what h is equal to. Now what I'm going to do is I'm going to take this volume formula and I'm going to replace the h with what it's equal to. That's what we just found a second ago. So now all I've got to do is simplify it, and I find out that the volume is also equal to this, which is what they wanted me to show in part B. So now I've got this, and I'm going to find the derivative. I'm going to make the derivative equal to 0, and then I'm going to substitute that in to find the volume. So first I find the derivative using the power rule. That gives me this. I realize that x cannot be negative. So anyway, I know when I'm finding a stationary point, the derivative has to equal 0. So I just make my derivative equal to 0. And then I have to solve for x, which I'm just going to multiply everything by 2 and then get x by itself. Keep in mind that when I square root, I get a plus or minus, but this has to be positive. So I'm only going to use the 5 square root of 6 over 3. All right, so now I'm going to substitute this x value into the original equation to find the volume when x equals this value. And all I do is substitute it in, and I'm going to find out that the volume is going to be 68.04 when x is equal to 5 square root of 6 all over 3. And then it wants to know, determine whether it's a stationary value, maximum or a minimum. Well, the second derivative, all I got to do is use the power rule for the first derivative, and that's going to be 2 times negative 3 halves, or negative 3x. And then if I put in a positive value, clearly it's always going to be negative, and if it's a negative, then it's going to always have to be a maximum. So that takes care of this. In this next problem, we've got a solid cylinder inside a sphere, and you'll notice that they want us to express r in terms of h. They want us to show that the volume is equal to 5 pi h minus 2 pi h to the third, and then find the value of h, for which there's a stationary value for volume, and then determine the nature of the stationary value. So let's keep in mind a stationary point is a maximum or a minimum. We're going to rewrite this formula so it only has two variables, v and h. We're going to find the derivative, then we're going to make the derivative equal to 0, and we're going to find the x values where that derivative is equal to 0. And then we're going to find the second derivative and substitute it in so we can determine the nature. All right, so let's get started. First, notice this point right here is the center, and if then I've got this h here, because if the whole cylinder's height is 2h and that point in the middle is the center, well then that line I've drawn must be h. And it's a right triangle, so I can use the Pythagorean theorem and say that r squared plus h squared is equal to 5 squared, and then I can find out that r is equal to that. So now all I've got to do is substitute what r is equal to into the volume formula, which is pi r squared times h. That's the volume of a cylinder. And then I'm going to have a volume formula that doesn't have r's, it only has h's. Now keep in mind it's a little confusing with the pi, and we're going to leave the pi sign so we can keep the answer exact, but pi is not a variable, pi is a number. So here's our volume formula, and it's going to be in terms of h. So now we're going to find the derivative using the power rule. So remember, this is going to be 1 times 50 pi, that's 50 pi, and then 3 times negative 2 pi, that's negative 6 pi, and then we're going to subtract the exponent. 3 minus 1 is 2. We're going to make it equal to 0 now, and so then all I'm going to do is get the negative 6 pi h squared on the other side. I'm going to get h squared by itself, and then I'm going to square root both sides, and I'm going to find out that h is equal to 5 square root of 3 all over 3. So now that's the h value. And what I need to do is figure out what the nature of this stationary point is. So I find the second derivative. And so the second derivative is going to be 2 times negative 6 pi, or negative 12 pi, and then times h. Well, a negative times a positive, the height has to be positive, is always going to be negative. So that means the stationary point must be a maximum. So now we're going to switch gears. We're going to look at rate of change problems. Now keep in mind that the slope of a linear function is often referred to as the rate of change, and it's constant. But if I do the derivative of a y equals mx plus b, it's going to be m. So I guess the point is that derivatives can often be referred to as a rate of change for a different value in terms of another value. So let's look at the problem. A couple examples. In this first one, h is equal to 1/5 pi squared. Now that's find the rate of change of h with respect to t when t equals 2. So basically what I'm going to do is I'm going to find the derivative of this function, and then I'm going to substitute 2 into it. So the derivative of h equals 1/5 t squared is 2/5 t. And now what I'm going to do is substitute the t is going to be a 2. So when I make the t a 2, it ends up being a 4/5. And in this case, instead of finding a slope, which we usually do with derivatives, we found the rate. And the rate is going to be 0.8 when t equals 2. So now look at this problem here. So they give us this equation with volume, or v, in terms of t. And they want us to find the rate of change of v with respect to t when t equals 4. So the first step is going to be use the power rule and find the derivative. And once I've got that, 4t minus 3, I'm going to substitute in the value of 4 wherever I see a t. That gives me the rate of 13. And that's all there is to that one. Now you can see some of these are pretty straightforward. This next type is going to be a little more complicated. When we've got connected rates of change, well, typically in these kind of problems, what's going to happen is you're going to have a rate of y over time, and then maybe x over time, and then you're going to have a derivative. And what's going to happen is we're going to use this formula here. You'll notice how the dx's both cancel out, giving us change in y over the change in time, or a rate of y. So let's look at an example. In this problem, they say we've got a point, and it moves along the curve with this y equals x plus square root of x 2x plus 3 in such a way that the rate of increase of x is constant at a value of 0.06 units per second. Find the value of the increase. All right, so notice how we've got in these problems 3 rates. We've got the rate of y changes over time, the rate x changes over time, and then we've got this derivative. So generally in these types of problems, they'll give you, or you can figure out 2 of these rates, and then you use the equation to the left to find the remaining rate. So let's see here. It says the rate of increase of x is constant. So that's the change in x over time. That's 0.06. They tell us that rate. And then they say that they find the rate of increase of y. So that's the change in y over time. We don't know what that is. So that's what we got to figure out. So then you'll notice how it says that we want to do this when x equals 3 at this instant. See, and that's looking like a derivative. So we take the function they gave us, we're going to change the square root and raise it to the 1/2 power, so we can go ahead and use the power rule and then the chain rule to find the derivative of this. Using the power rule, the derivative of x is just 1. And then I'm going to take 1/2 and move it to the front, multiply it, reduce the exponent by 1, and then multiply by the derivative of the inside, which is 2. And see, now all I've got to do is simplify, multiply by 2. I'm going to end up with 1 plus 1 over square root of 2x plus 3. Now, all I've got to do is find out what, if I'm going to take, that's my derivative, I'm going to substitute 3 in for x, and I'm going to find out that the derivative equals 4/3 when x equals 3. So now I've got 2 out of the 3 pieces of information. I know that the change in y over change in x, or the derivative, is 4/3, and I know the change in x over time is 0.06. So I'm going to plug that into this equation, and you'll notice that when I multiply these two together, I'm going to get the change in y over time, or the rate of y, and it's going to be 0.08. And then the rate of change would be expressed as y is equal to 0.08 units per second. Now, it doesn't always have to work out this way. It could have been that we were looking for the change in x over time, and we knew the change in y, and we could figure out the derivative. What happens is that kind of changes things a little bit. The equation that you see here, the change in y over time equals the change in y over change of x times the change of x over change of time, that's the formula we're going to use for this kind of problem. And you just plug in what you know and then figure out what you don't know. We'll see some of those when we do some of the other problems. All right, so thanks for watching this. I hope that it helped.